Ma'am, mag-admit na po ba kayo ng mga tao sa meeting room?
Yes, please.
Sige po. Sige po.
Thank you.
Face the breaking point, and I don't care if I go down with it the way I see it, there's no point, cause in the end it's only down to us. There's no love nor love, and I don't wanna admit we're at the breaking point. Don't need no blood scars, it's not a false alarm. Before it's breaking us, let's face the breaking point. The breaking point. Face the breaking point. Just get it done. Face the breaking point. Don't need no blood scars, it's not a false alarm. Before it's breaking us, let's face the breaking point. The breaking point. Face the breaking point. Just get it done. Face the breaking point. I left things unsaid, and you cannot forget how my mistakes haunt us, but do they really daunt us? Your tongue can be sharp, cut me close to the heart, but we can master the art. And the thing is that these scars are scary, but they are just small scars. We should never be afraid of them. Even I know when we are too far apart, everything just falls apart. So I just close my eyes and dream about our kids and how they're running around. Won't you come and lay down next to me? Close your eyes and we'll be free. I'll keep my head high while we're crossing the land. With all the miles we lay down, it's gonna take us some time, but I won't give up, though I know it is tough. We need to break our patterns. It's better now than after we have drifted off too far. Let's tear down these walls our destiny has called. We're walking down a path, and the wind will change at last, like a song about our past. So I just close my eyes and dream about our kids and how they're running around. Won't you come and lay down next to me? Close your eyes and we'll be free. I can see the point.
Really good.
Pointing fingers, come on, let's rejoice of what will come. I have made the choice of thinking bigger, 'cause you are all that I need, you are all that so I just close my eyes and dream about our kids and how they're running around. Won't you come and lay down next to me? Close your eyes and we'll be free. gonna get stronger. I'll be okay, just give me a little bit longer. Yeah, we're gonna win the struggle we're in. It's never goodbye, it's never goodbye till it's over. Come back to love. I was so crazy to lose you. Just come back to love. Let's never do what we used to. Leaving without saying, teasing without playing. I've had enough. So come back to love. I hope you're all good. I hope you're all good where you are now. It's probably too late, but here I am reaching my arm out. I want us to win the struggle we're in. It's never goodbye, it's never goodbye till it's over. Come back to love. I was so crazy to lose you. Just come back to love. Let's never do what we used to. Leaving without saying, teasing without playing. I've had enough. So come back to love. I hope you're still with me. This time will be different. Let's make a decision now. So come back to love. I was so crazy to lose you. Just come back to love. Let's never do what we used to. Leaving without saying, teasing without playing. I've had enough. So come back to love. So come back to love.
Hey, do you remember 20-something years ago? Those cold nights in December and the sound of the falling snow. The fireplace warming us, the VHS movie box, your old broke down touring bus, and not a single cloud in the sky. If I could go back in time, I'd pack my bags right now. If I could play back, rewind, I wouldn't think twice. A pair of jeans and a dusty shirt, we didn't have a dime. No, you and me were poor as dirt, all we had was time. Hey, do you remember sneaking out in the night? Me playing the Fender and you singing, oh, it's alright. Beating hearts full of lust, shiny stars over us, just a dream guiding us, and not a
Thank you very
single
much.
cloud in the sky. If I could go back in time, I'd pack my bags right now.
Hello.
If I could
Oo.
play back my life, I
How to stop if you want to like the sound of
Good morning, everyone. It's great to have you all back this morning for the second day of our World Expert Lecture Series. For this time, it will be a hybrid setup. We are joined by a live audience hosted at the audiovisual room of the National Institute of Geological Sciences, and we are also hosting participants in our Zoom platform. Again, once more, we are thanking you for your active participation. We also would like to thank the following groups and organizations for making this event possible. The Office of the Vice President for Academic Affairs of the University of the Philippines, the National Institute of Geological Sciences, the Society of Economic Geologists, the Geological Society of the Philippines, and the Rush Urgent Working Group. Before we begin our event, we would like to remind everyone of some house rules. First, for our virtual participants, we are kindly requesting you to keep your microphones and cameras off during the duration of our lecturer's presentation. For our on-site participants, you may start asking questions after the presentation of Professor Hattori by approaching the microphone positioned at the center of our venue. For our Zoom participants, you can either virtually raise your hand and wait for us, the moderator, to acknowledge your name and unmute your microphone. Quickly, please state your name and affiliation before asking your question. Alternatively, you may enter your questions using the Zoom chat box. Today, we are once again delighted by the presence of Professor Keiko Hattori from the University of Ottawa, Canada, who will talk to us about magmatic and hydrothermal processes related to mineralization, alteration, and exploration. To introduce our speaker, may I call on Dr. Betchay Dapayot, professor from the National Institute of Geological Sciences. Ma'am?
Thanks, Nico. And good morning, everyone. Welcome to the day 2 of our World Expert Lecture Series. And it is with honor and pleasure that I introduce again our guest speaker for today. So Dr. Keiko Hattori is professor at the University of Ottawa in Canada. Her work is mostly focused on geochemistry as well as ore deposits. Keiko and her students examine element transfer in subduction zones and mineralized hydrothermal systems. They utilize a variety of mineral deposits and their exploration methods, including epithermal, orogenic gold, as well as porphyry copper, among others. Given her significant contribution, Keiko is an elected Fellow of the Mineralogical Society of America and Fellow of the Royal Society of Canada. She is also presently Associate Editor of Nature Scientific Reports and Economic Geology, and is currently the International Exchange Lecturer of the Society of Economic Geologists. We are honored to have here today Professor Keiko Hattori. Let's welcome her with a round of applause.
Thank you. Thank you, Bachai, for such a great introduction about myself. Okay. So today, I prepared, can you hear me this one? Okay. So today, I prepared a lecture for the review of magmatic hydrothermal processes related to metallic mineralization, alteration, and exploration. Considering the location here in the Philippines, the emphasis of metallic mineralization is copper and gold. I will touch on tin tungsten, but mainly I talk about hydrothermal activity related to copper and gold. So this is the outline. First, talk about several deposits associated with ferrosic igneous rocks and the character of magmas. Character of those magmas associated with mineral deposits. Those magmas are able to transport metals from the source area to upper cluster levels. And how those magmas can discharge magmatic hydrothermal fluids, and which metals are partitioned from magma to fluids. And then I'll talk about magmatic fluids separate into liquid and vapor at shallower level. And again, some metals are preferentially partitioned to liquid and some are into a vapor. And also I briefly may talk about acidity of fluids because that is very important for the ability for metals to be transported and how metals may be dissolved in hydrothermal fluids. And because many mineral deposits contain quartz veins or quartz or silicification. So I'll talk about silica, how precipitated, and also hydrothermal alteration by magmatic hydrothermal activity. And this has a direct implication how those magmatic hydrothermal deposits may be found through exploration. How alteration is important in finding exploration. That's I will discuss. So we know porphyry copper deposits are associated with ferric stocks like porphyry copper moly, porphyry copper gold, and the tin, and also tin tungsten deposit. Glycine develops in igneous rocks and the skarn, and also high sulfidation gold deposit, high sulfidation epithermal type gold deposits develop overlying area of porphyry copper deposits. Therefore, based on spatial association and also that they are with inclusion studies, we know high sulfidation epithermal type gold deposit are directly linked to porphyry type deposit. So that's what I will talk about. And so this one I will talk very briefly because yesterday also I mentioned what kind of magma can transport metals from a source. And not all magmas are capable to produce metallic deposits. And those magma are called fertile magma. So what are the important factors? Of course, magma source is important because of like partial melt from a lower cluster or melting of sediments. They have very reduced conditions, oxidation conditions, therefore not capable to transport lots of copper or gold, but very good, perhaps tin, tungsten, and some are produced in astenospheric mantle. Again, that has a big implication because astenospheric mantle has a very reduced, again, oxidation condition. So then oxidation conditions affect solubility of metals sulfur. And water content. This is important because if magma is very dry, it is very difficult to produce magmatic fluids or magmatic hydrothermal activity. So already, this one I showed, for example, sediments. Sediments almost always contain small amount of organic matter, meaning then when graphite is present, then at those high temperatures, those oxidation conditions, or oxidation condition is buffered by graphite, because graphite in oxidized become CO2, meaning is when graphite is present, graphite keeps oxidation conditions low, even lower than ferrite, magnetite, quartz buffer. That's important because sulfide is stable even around ferrite, magnetite, quartz buffer. And so sulfides are stable under low FO2, meaning is such magmas generated or incorporating some organic matter have a very low FO2. And that has a big implication for the transport of sulfur and metals because this is a compilation of the oxidation conditions of some porphyry copper deposit and also, for example, arsenic basalt. Porphyry copper related or porphyry copper gold related igneous rocks have a very high FO2, more than 100 times or 2 orders of magnitude of oxidation conditions. Obviously, these porphyry copper released magmas did not assimilate many igneous rocks with organic matter. So they showed like a magma source, like lower crust or even upper mantle. Sulfur metals are in a sulfide. To incorporate those sulfur and metals, you need to have magma with oxidized condition. And as I just remind you that those, if organic matter is present, organic matter keeps oxidation condition very low. And so this is solubility of sulfur and oxidation conditions, meaning is you need to have oxidized magma to have a large amount of sulfur. Most of the copper deposit, copper occurs as sulfide, meaning is that you need to transport magma. You need to transport sulfur from the source to the upper crust. And because sulfur is sulfate in oxidized condition, therefore solubility is very, very high, 1 order of magnitude higher in oxidized conditions. And this shows, for example, solubility of that gold and copper in the magma. This is the oxidation conditions. As you can see, oxidized magma can carry lots of gold and copper. Again, several far more than this is a logarithmic scale, meaning is almost logarithmic order of magnitude, higher amount of gold, copper in oxidized magmas. And also, as I mentioned, oxidized magma can contain lots of sulfur. When you have lots of sulfur, also other metals like copper and gold are enhanced. So again, when you have oxidized, magma can have lots of sulfur. And when you have lots of sulfur, again, lots of copper, lots of more gold can be dissolved in magma. Therefore, magma generated in a lower crust or lithospheric mantle, they can transport those sulfur, lots of copper, gold from source to upper crust where magma solidified. Okay, so this one just showing a previous one was copper. This shows gold. Again, that when sulfur is high, amount of gold dissolved in that magma is very much enhanced. So this is very important. If magma doesn't contain much gold or copper, it's difficult to produce a deposit. So also that magmatic hydrothermal activity, meaning is magma must generate hydrothermal activity. Of course, in upper crust, some groundwater, but magmatic fluid to be generated with lots of metals, magma had to have water, and that magma had to separate water from magma. Because during a crystallization, most crystals, like for example, hornblende, yes, contain maybe 1% of water, but not much water in a crystal. That meaning is during differentiation, crystallization, water content increase in magma. So more crystallization, higher amount of water in a melt. Also, this shows solubility of water in a magma. You can see this is oxidation conditions, and this is water, solubility of water. Oxidation condition doesn't affect much of solubility of water. But when you look at here, this is a x-axis is a pressure, and this is equivalent to 10 kilometer, 20 kilometer, and this is a 1200 degrees. This is a 1000. You can see very similar. Higher pressure, deeper level, magma can dissolve lots of water. Example, and also composition of magma, not that different. And some are 2.38 sodium, meaning is more mafic. To that, sodium 6%, fairly almost alkaline. And then that water solubility, not significant different. Yes, some difference, but not different. Most important factor influencing solubility of water, how much water can be magma, is a pressure, meaning is a depth. Meaning is when magma is going up in a crust. For example, if deep level, like even 20 kilometers below the surface, magma can dissolve even 10 weight% of water, there are lots of water. But then when magma is ascending to magma is ascending, for example, 5 kilometers below the surface, only less than maybe 3 weight% water can be dissolved in magma. That meaning 10 weight% of water to 3. Large amount of water had to get out. And then when you look at this one, closely around here, sharp decrease in the solubility of water. This meaning is water is released from magma, or magma produce immiscible aqueous fluid at shallow level. And that happens very, very shallow level. This is another way of that looking at, now that x-axis is water content, and this is pressure, the same thing. Basically, at a shallow level, very sharp change in that water solubility. So when water is released from magma, what happens to the rocks? It is now fairly well documented. Many felsic igneous rocks, cupola part, roof part, you see those textures of quartz together with the feldspars you may have seen. And this is called unidirectional solidification temperature, not unidirectional solidification texture. And some people call brain rock because it looks like outer part of brain. And texture may be straight or sometimes curved. So this is explained by because magma doesn't have a totally flat outline, and the water may be accumulated into that slightly upper part because aqueous fluid is lighter than melt, less dense. Therefore, tend to accumulate in those roof part, and quick solidification, crystallization of minerals, and producing such texture. This is direct evidence. Yes, water escaped very quickly at some shallow level. And as I said, if you are interested, Dagger Carving has several of those papers and photographs showing those unidirectional solidification textures. Maybe you can look at it. It requires a bit of good eyes, but there are many locations we find such textures. Okay. So now, what happens when water is released from magmas? Not only nature doesn't like a pure system. When water is coming out, some elements, metals, which have affinity with the water, likes to go together. This is a very different from chemistry laboratory. Chemistry laboratory, you have a pure water, pure silica, pure something. But in nature, nothing is pure, always something. And so very important to understand some affinity of some elements. So again, that I will talk about when water is released from magma, what happens to other elements? So chlorine, it's very easily to understand. Chlorine is not easy incorporated amphibole or therefore this is a partition factor crystal to melt. Basically, this is far less than meaning is most of chlorine will stay in a melt, doesn't go to crystal. So how about here? Now, partition factor between fluid and crystal. And then if you have a fluid, those chlorine likes to goes to fluid. That's fairly kind of intuitively understanding because chlorine likes to be with water. And again, also that this is chlorine in a melt, chlorine in a freeze. You can see if you have a chlorine at say 1% or 0.6 such, chlorine in a fluid will have a much higher concentration, meaning is chlorine in a magma goes into aqueous fluid. Okay. This is important because later I will talk about how metals are transported in aqueous fluids. Metals likes to be also affinity with chlorine, form metal chloride complex, very high solubility compared to pure metal cation. So, and also this is now sulfur. Look at this is a fluid to metal, fluid to metal partition, very high values. This is a amount of FeO, beginning meaning is a ferritic rock, rhyolitic rock. Usually FeO is about less than 48%. And then meaning is that when magma generate ferritic magma generate aqueous fluid, most sulfur move to aqueous fluid. Okay. So in the case of slightly more mafic, less so, but still we are talking about ratios of 100 or 50. So again, many chlorine now goes into aqueous fluid. Now sulfur also going into aqueous fluid. So also that this shows those partition, again, sorry, chlorine, deeper level, more chlorine goes into fluid. So now, how about that metals? This is copper. Copper, this is the amount of fluid to melt. You can see copper. Again, that this is a more rhyolitic one. This is more mafic. So you can see very larger proportion of copper going into aqueous fluid. Don't stay in that melt. Okay. And also chlorine, because those are experimental work. Sometimes don't use chlorine, sometimes don't use sulfur, but when you add chlorine into a system, this is now fluid to melt. Zinc and lead, less so, but still that when you have chlorine is present in that system. Most of those zinc metals goes into aqueous fluid. Fluorine tends to stay in a melter because fluorine has a very similar ionic radius. Charge is different, but similar. Therefore, metals with affinity with fluorine remains in a melter. This is not the case for copper and gold, but you can see fluorine in a melt, fluorine in that fluid. Still some goes into that fluid, but still that lots remains there. We are talking about numbers of 2, 4, 6. Like copper was more than 100, 200. So, for example, niobium tantalum. We don't hear niobium tantalum hydrothermal mineralization because niobium tantalum are only of those metals. They like to stay in that melt. Sorry that this is a bit. Sorry, this is a amount of HF. Meaning is when fluorine, lots of fluorine is present. Niobium tantalum likes to be together with niobium. Therefore, again, fluorine likes to be in melt. Meaning is that niobium tantalum remains in a melt. Later in a pegmatitic phase, then niobium tantalum accumulate in that pegmatite. So this is kind of a compilation. You can see fluid to melt. This is different melt metals. Copper preferentially goes to aqueous fluid. Molybdenum preferentially goes to aqueous fluid. Zinc, But like sodium, zirconium, rare earth elements, they don't like to go to aqueous fluids. They tend to remain in that melt. And we know that because those metals are often accumulated in a very residual magma in a pegmatite. Okay? Explains very well because they do not go out to aqueous fluid. And so this is a more through figures, niobium, cerium, uranium. Also, again, that we know uraninite is accumulated in a pegmatite. And so natural observation is consistent with a farm experimental result. Well, I can skip to that one, but you can see again that tungsten, and this is a chlorine, and the tungsten likes to be in a melt, and therefore concentrated in a pegmatite. Doesn't move. Yes, and also rare earth elements. You can see this ratio is 0.02, 0.04, 0. So but you can see deeper level, more rare earth elements enters the fluid, but still most of those rare earth elements stays in a magma. Okay? So if you have those high D values, meaning is that kappa was more than 100, meaning is during a crystallization of a melt, concentration of melt decrease, because when that solubility, for example, if water is 48%, and when aqueous fluid is generated, right away kappa concentration melt decrease. On the other hand, some metals like rare earth elements and also tungsten, because they stays in the melt, therefore concentration in the melt rather increase. Okay. So I think part one is finished. So now I think part two. But I have a bit of time if you like to have questions.
Before we proceed with the second part of Professor Hattori's presentation, does our participants, both on-site and virtual, have any questions?
Jill has a question.
Yes, Professor. Thank you for the talk. Speak about on fluorine. The fluorine is what we can present in. If it is in benefit magma, is that correct? Fluorine.
Always fluorine is present, and that's the reason when you do analysis of apatite always contains fluorine. And as a matter of fact, during, for example, that immiscible separation of aqueous fluid, fluorine tend to stay in the melt. That's the reason apatite contains more fluorine than chloride. So often that's fluorine-chlorine ratio, the apatite is used when this separation happens.
So usually in the Philippines, we have mostly like dialytic or low like input. So then, what happens to the fluorine in that case?
Fluorine, the total amount of fluorine is not huge usually. And therefore those fluorine is usually incorporated apatite first, and also incorporated in that amphibole. Igneous amphibole contains not a huge amount, but always a small amount of fluorine. So those hydrous minerals take fluorine because very easy to, replace. Fluorine F minus is very, very similar to OH. So, and also biotite, sorry. I forgot. If you have a biotite contains fluorine. Several of those are some granite, and sometimes fluorine is high. Therefore, those fluorine is accumulated in a pegmatite phase.
Thank you, Professor Hattori. We have a question from our Zoom platform from Mr. June Angeles from the Geological Society of the Philippines. How do you explain copper plus base metals in reduced intrusion hosted gold deposits?
Yes, that always that as I showed that I'm talking how much water can be released from magma. Through that reduced magma, of course, some reduced magma can produce gas fluid. And therefore, those reduced fluid can incorporate the copper. The amount of copper and the sulfur at the source for those reduced magma may be small, but still copper and the sulfur is there. Like, for example, when you look at oceanic basalts, salts always contain about 1,000 or slightly more than 1,000 ppm sulfur, and also that usually 60, 70 ppm copper, meaning is always there. Then that even reduced magma contains small amount of copper, sulfur, and when aqueous fluid is separating at a shallow level, they take copper sulfur from magma. Therefore, yes, still possible to make porphyry copper deposit, but whether that is a large porphyry kappa deposit or not is a different story. And also that my student worked on a Gibraltar porphyry kappa deposit in Canada. We found several of those pulses of porphyry kappa mineralization. Some are not highly oxidized, but because several times mineralization happens, therefore this repeated injection of slightly not highly oxidized magma generated economic deposit. So that could happen.
Thank you, Professor Atori. Do we have a question from our live audience?
Example, versus in oxidized elements. More iron occurring in oxidized.
No, they are usually when you look at iron, x-axis and solubility of sulfur, usually more if you have yes, iron more sulfur, yes. But that is in a reduced condition. Yes. But still that we are talking about 1,000 ppm, 2,000 ppm, 3,000 ppm. We are not talking about percent order sulfur in oxidized magma.
What makes the parameters to have a high eventual gravity minimum?
So through several studies, we know mantle wedge below subduction zones, oxidation conditions are quite different. Meaning is what subducted in that subduction zone affect what kind of that oxidation, because magma is generated in that mantle wedge, and that's affect their what kind of oxidation condition. But of course, for example, some tin tungsten deposit, some are S-type or so-called another A-type granite. They were generated by mostly those lithospheric mantle with lots of sediments. Again, that are fairly reduced. Therefore, what is a source of that magma is very important. And then at what kind of subduction zone, I don't go into this talk, but for example, we know, for example, that therefore lots of sulfur in the magma. On the other hand, like Japan, most of that volcano doesn't contain much sulfur, doesn't contain much not oxidized. So what kind of subduction system? Where is the magma source? That's affect those oxidation conditions. And obviously when you have lots of those sulfate is subducted, and then that sulfate is fairly mobile, that may affect oxidation conditions. And so it may be interesting to see western side of Luzon, eastern side of Luzon, what kind of subduction system. Yeah.
I'm sorry. Just another question, just very brief. For the UST, for the USTs, the Unified Certification
Yes.
Textures, I'm just curious if there are the USTs confined in a particular alteration type or confined in a particular porphyry stock stage. Thank you.
So far, for example, those unidirectional solidification textures are also documented not only porphyry kappa, porphyry kappa mori, and also tin tungsten deposit. And so I think that what is important is a shape of morphology, and those when shape is this way, more aqueous fluid accumulated this area, and so that's more generate those focused fluid release, and but also that for example that I visited some of the places in in Australia, and unless you have a very good eyes, this is a texture, because sometimes more deformed, so you may not recognize. But when you see these coarse and feldspars and fine grained, those are layering is a unidirectional solidification texture. Then you may find more in many places. Yeah, but this is important because the meaning is they are, especially like a Paleozoic terrain and the older one, this was up, because sometimes tilted now, this was up, and that was a place where focused aqueous fluid release. Thank you. I think I have a part 2, part 3, so maybe we may have to go. Yeah, but of course, if you have a
I think we have a last question from one of our Zoom participants named Leofer Dagdag, a consulting geologist. He asks, what ligands for gold or copper are common in mantle-derived magmatic sources and also in crustal-derived sources?
what is a pardon, kappa?
The ligands. What ligands for copper or gold are common in mantle-derived magmatic sources and also in crustal-derived sources?
The difference in gold content, or I don't fully totally understand. Okay, so usually sedimentary rocks contain more fluorine than chlorine. Therefore, sediment derived or crustal derived, those magma contain usually more fluorine, usually, and compared to chlorine. That is usually the case. That's the reason S-type granite often contains high fluorine. So shall we go to?
Thank you, Professor. So we'll now proceed with the next part of our
Yes.
lecture.
So after that, part 2, part 3, probably or lots of time for question. Yes. This is now part 2. Okay. So now I explained chlorine tends to partition into aqueous fluid. So this is a diagram showing when melt NaCl and H2O ternary diagram. When you have of course lots of water, melt water, this is continuously, so melt and vapor simply meaning is H2O may be present, but if you have lots of salt, it may create also melt and salty aqueous fluid. So before going further, since this is a lecture for students, just I like to explain several things about the property of water. So everybody knows pure water has a critical point, 374 degrees. After critical point, water is not a liquid or vapor, critical fluid. So people think, oh, strange. We are talking about some magmatic fluid, aqueous fluid, 500 degrees, 600 degrees. How come it is possible? The reason why is this is the temperature here, and this is the pressure. So this is a salt saturated fluid, basically salty water. Salty water can be liquid. This is boiling point, meaning is it is if you have lots of salt, 500 degree or even 600 degree, liquid is possible. I think that is very important because liquid has lots of capacity. We know that the liquid moves around along fractures. Liquid can dissolve lots of things, move from one place to the other. So that is the first point. And this is a bit of complex, but what I'm trying to show is that this is a temperature, higher temperature. This is a amount of salt. And so the system pure water, meaning is that no salt, therefore this is equivalent to this left side. And the critical point is here. But if you have salt, this curve change, okay? And just so critical point goes up. That is a way. If you are very interested, maybe you can look at geochemical cosmochemical actor, Drisner's paper. But important point here, if you have lots of salt, now even 400 to 500 degree salty water is possible because of critical point goes up. So this one looked at a slightly different way because a three-dimensional diagram is a bit difficult to comprehend. So this is just a temperature and the pressure and vapor, liquid, and halide coexisting. What is this one? So this is the same as my two slides before. And here is now slightly lower temperature, like 300 degree. And up to 300 degree, this vapor, liquid, halide, salt are coexisting. As you can see, no problem to have liquid water, liquid salty water at 300, 400, 500 degree. So now in nature, what happens? So again, that this is showing those pressure, this temperature, and this is vapor. This uses vapor, but vapor and NaCl. And this is a two-phase region, two-phase regions and different salt content. So for example, this is 10 weight percent salt. This is a 5 weight percent. And this is, say, for example, 1 weight percent salt. And this is shows the red one is a granitic solidus. So evaluate, for example, when granite is solidifying, say, for example, maybe 4 kilometers below the surface or 6 kilometers below the surface. What happens to that aqueous fluid? And for example, just to look at when granitic magma solidifying maybe 6 kilometers, so about here. So this fluid is above this critical curve. And so meaning is that the fluid has one critical fluid, not a liquid, not a vapor, critical fluid. So then, so this one phase critical fluid is trapped, say, in quartz fluid inclusion. And then right now we see at room temperature, that is still one phase. But then when what happens, for example, maybe 10 weight percent NaCl and 5 kilometer below the surface, then look at a slightly different way. This is now NaCl. So this is the x-axis is temperature, this is pressure. Now look at just pressure and sodium. So basically going downward, going down in temperature. So what happened is this one phase, and then now room temperature, looking at that is originally that one phase. But then if you have, say, trapped, say 4 kilometers below the surface, now granite solidus, now aqueous fluid separated. This aqueous fluid now cannot be one critical fluid. Now separating into salty, very brine, salty fluid and vapor. And because this is below the critical curve. Because there's a granitic solidus needed to, because now solidifying, so aqueous fluid is separating. So this aqueous fluid separated, right away separated brine and vapor, because below the critical point. So this is a bit upside down, meaning is looking at from surface to a deeper level. So what happened is those fluid generated in a magma. This aqueous fluid contains lots of salt. Could be 10, could be 8 or something. Those fluid goes up, ascend. And this fluid had to separate to liquid phase and vapor phase. And this liquid has lots of salt, meaning the brine. This vapor, because the vapor cannot contain lots of salt. So not much salt. So this has a very important implication, because now we learned magma when ascend to shallower crust, this magma had to release water because it cannot be accommodated within magma. This now that shallow level, because aqueous fluid is still less dense compared to magma, therefore ascend, could separate from magma. And then when during the ascent, needed to separate very dense brine and very light vapor. So again, that magma is more dense than the aqueous fluid, and this aqueous fluid ascend, and then a denser salty water and the vapor separated. As we know, vapor is less dense, meaning is that so critical slide. Bulk salinity is such, but so in that now, when you look at the crystals, you see they can hypersaline fluid and just vapor. So now that I will look at what is then that happens. What? This is the reason, for example, when you go to many porphyry copper deposit, this was a long time ago, I visited Panguna deposit in Bugenberg, and entire pit, you can see lots of breccia. Because now magmatic fluid going up to that very shallow level, now separating a vapor. Vapor meaning is less dense, huge volume, making lots of those brecciation. Actually, I was very surprised from far away. You don't see it, but close by, large breccia is present. Again, that because fluid release and this fluid separation to vapor cause those volume expansion, brecciating rocks. Ups. So what now happens? Now magmatic fluid separated into brine and vapor phase. Again, some metals likes to be more brine, or some metals likes to be, or some element likes to be in that vapor phase. So what happened is that this is 1-to-1, and like for example, copper, brine has maybe 1000 ppm, and the vapor phase has just over maybe 200 ppm, less than 200 ppm. Meaning is that many metals, useful metals like zinc, copper, molybdenum, they likes to be in that liquid, not vapor. A significant amount of those chlorine, like boron and arsenic, those volatiles may go to significant amount into vapor, but most metals stay in a brine. So that's important. So how about the sulfur? So again, this is oxidation conditions. Those mentioned most arc magmas could be about that. And the gaseous sulfur phase could be H2S, SO2, or could be that H2SO4, but basically SO2 and H2S. This SO2 react with H2O, disproportionate reaction, producing H2S and the H2SO4. So now, quite important, this is now producing H2SO4. So we know sulfuric acid, H2SO4 is a sulfuric acid. Therefore, very acidic. However, if high temperature, H2SO4 or even HCl, they do not dissociate. They stay as H2SO4. Therefore, not that acidic. However, lower temperature, what makes acidic? I'm really sorry, I'm sorry. What makes acidic is producing H plus cation. So lower temperature, those are dissociating into making H plus. That's the reason that now lower temperature, now H2SO4 make very acidic fluid. So this has a bit of implication because now we know vapor is producing acidic fluid at a lower temperature. So now we look at how metals are transported in a fluid. Basically, three types of metals transport. What happened now? Basically, three types of metal transport. Metals can be transported as a chloride complex, or Saya complex, or complex with water. But before going into metals, I like to talk about quartz may precipitate. Always quartz veining is abundant in many mineral deposits. So this is a millimole of SiO2. As you can see, higher temperature, more silica, and this is a CO2 content. And you can see pressure subtle difference, but not that different. For example, 4 kilometer or 8 kilometer, so at a given temperature, solubility of silica is the same. And whether 4 more % of CO2 a lot or no CO2, again, when you look at, for example, temperature, say 350 degree, 350 degree, not that different. Meaning is that when you look at these two, right away we can tell what is the most important factor to precipitate quartz is a temperature. Looks like a storm. Storm is coming, a rainstorm. So from this one, you can tell if you have a quartz vein, meaning is that that is a place where temperature decreased. Okay, not a temperature increase, temperature decreased. That meaning is that this was a place where hot fluid discharge. Okay? So this is an easy way to look at it, solubility, temperature. Temperature is a major factor, and quartz crystallize during cooling. Sorry that, yeah, this was missing. 3 main types of soluble metal complex. It is a very, for example, copper, zinc, lead, cadmium, silver. Solubility as a simple cation, like copper 2 plus or zinc 2 plus, very low. But they make a complex, chloride complex. Chloride complex is soluble. Or molybdenum, OH complex, or gold makes with H2S or HS minus to make complex to dissolve. So different way of the dissolution has some implication how those metals may precipitate. So for example, that dissolved form of copper doesn't matter what temperature, not that different. Whether this is a proportion of that copper chloride CuCl2 or CuCl3. So you can see lower temperature, more CuCl2, and if you have lots of chloride is present, because lots of chloride, therefore more CuCl3, more chlorine is combined, that is more abundant. So, but whether 150, 250, 300, not that different. Basically, chlorine is soluble as a chloride complex far higher amount than that simple copper cation. Okay. But the gold is a bit different. This is a salinative gold, salinative fluid. This is amount of gold. This is a 400 degree. You can see gold is mainly gold HS complex at less than maybe 10% of salt. But then if really chlorine is very, very high, gold makes a gold chloride complex. But we know, for example, many gold deposits, especially the hydrothermal type deposit, less than 400 or less than 350. You can see this is a gold HS minus complex. is very important for transport of gold. However, if, for example, porphyry copper environment, high temperature, maybe gold chloride complex in a brine, that's maybe important. Yeah, this one is just showing that the environment where most epithermal type environment, gold is transported as a gold HS minus complex. That's a very different from base metal. And this is the reason why, for example, if you have H2S, hydrogen sulfide is abundant, gold is more dissolved in not those solution. Again, not very different. This is oxidation conditions. Now copper and silver. This is now NaCl, KCl, 900 degree. More oxidized, yes, copper dissolved and the silver dissolved. But then at I'm really sorry, just slightly mixed up. So this is now gold solubility, and this is now oxidation conditions. When the oxidation condition is increased, very different from copper and gold, copper and silver, because then oxidized conditions. Now H2S is not stable. H2S changed to SO4 or SO2. Therefore, in the case of gold transportation, highly oxidized conditions, then not much gold is transported. Okay? So that's maybe the reason copper, silver, and gold are separated in many deposits. As I mentioned, molybdenum is transported at OH complex, and therefore higher pH, meaning more OH. Therefore, OH is abundant in that alkaline solution, and therefore more molybdenum. Again, different metals have a different way of dissolving, meaning is a different way of precipitating. So again, this is the abundance of that molybdenum complex, and and not that different whether at 250 or 350 degrees. And in the case of molybdenite, and again, that the amount of chlorine is not that important because they are not making a chloride complex. Again, very different from copper or silver. But important molybdenum to become molybdenum cation. So slightly shifting subject. How long does it take for magmas to produce magmatic hydrothermal activity? I'll show those octady, because this is 5.5 million tons of copper, very significant mine. And this is the youngest porphyry copper deposit because it formed 1.3 million years. Meaning is that this does not take many million years to produce porphyry copper deposit. So this is octady's data, porphyry copper deposit. Using that ion microprobe, they measured magmatism zircon age shows 1.368 plus minus 0.045, 1.4, basically 1.4 million years. But then when you look at For example, that the age of mineralization by, this is a cutoff, rhenium, osmium, molybdenite age, again 1.3 million years. So 1.4 to 1.3, very, very short time, less than 1 million years, or almost 0.1, considering that error range, really that very, very short time, magma solidified, form of zircon, magma produced magmatic hydrothermal activity, and mineralization happened, copper mineralization happened. So another example is El Teniente. This is a large 130 million tons of copper, very large porphyry copper deposit in Chile. This is a 7 million, 6 million, 5 million, 4 million. Uranium lead zircon age shows several different intrusions occurred. Some are 6.5, some are 5.5, and some are even younger than 5 million years. So obviously that several stocks intruded into site in a very, very short time period. And then when you look at the hydrothermal biotite and elite, almost there's a continuous age spectrum. You can see that 4.57 million years already starts to have hydrothermal biotite and hydrothermal silicite elite produced. So this shows how magmatism and magmatic hydrothermal activity are usually very, very linked, and also that not only linked, in a fairly short time period, such large porphyry copper deposit formed. This is this is Massimo's compilation, and apparent duration. They did a very detailed examination of that zircon grains, because several of those hydrothermal activity is overprinting, and so single shallow intrusion had a very short, very far less than not 1 million years of magmatic hydrothermal activity. However, this intrusive center had multiple hydrothermal events, and also in a response to multiple igneous activity in intrusion, pulses of igneous rocks, and over 1 to 5. And also I mentioned some of there, we examined this is called granite lake batteries, very large batteries, more than 10 kilometers, all were diagram. And then when we did dating, some are close to 230 million years, but the mineralized one is 219, 213, 206 million years, meaning is that this was a site where magma came up to that very, very narrow, small area. Narrow meaning is still 10 kilometers in diameter. And then those, each pulse produced some mineralization. Because it was a fairly small area. Therefore, this several intrusion made as a sum, as a total economic mineral deposit. Okay? That happens. And also another example is a Bataan Arc, Philippines. but contains many porphyry kappa deposits and also coinciding with many volcanoes. Many volcanoes here due to the subduction of South China, where oceanic crust is subducting, producing a volcano, and also porphyry kappa deposit. And this far southeast of porphyry kappa deposit is again similar to Octedi, one of the youngest porphyry kappa deposit. And recent publication by, this was a couple of them. So recent publication in economic geology about very detailed alteration and geology of far southeast porphyry kappa deposit. Several intrusions, and those dating of the homeland suggest about 2 million years. And those porphyritic intrusions, and this is a high sulfidation gold deposit. I'll show you another better one. So igneous homeland is about 2 million years, and then that biotype is 1.4 to 3 million years in argon dating, and then at this this intrusion produced many magmatic hydrothermal activity. When we examined white mica is 1.37 to 1.22 million years. Again, at less than 1 million years, all those magmatism and magmatic hydrothermal activity and magmatic hydrothermal alteration and mineralization. Next one, I will detail. So, oops, sorry. Okay, so next several slides, I will talk about, so this is a porphyry kappa deposit, and this is a contour of gold and 1 ppm gold, and this is a contour of 0.5% kappa. So this is a porphyry kappa deposit, and also that now this is a Lepanto. This is far southeast porphyry kappa. This is a Lepanto high sulfidation gold deposit. So I will talk about this. How does the high sulfidation gold deposit formed in this porphyry kappa system? Okay? To understand this one, okay, so just remember this igneous rocks are ascending, producing magmatic hydrothermal fluid. This magmatic hydrothermal fluid separating, because this is shallow, separated into brine and vapor. And that vapor was very important for this high sulfidation gold deposit. So I will explain why. So just again, since this is a lecture to students, I like to talk about fundamental aspect. What is acidity? Acid meaning is more hydrogen. And therefore, room temperature, we know neutral pH is 7 because this is dissociation constant is 10 to minus 14. Therefore, hydrogen ion is 10 to minus 7. So HCl in a vapor, we already talked about chlorine goes to brine and also chlorine goes into vapor. So HCl in a high temperature stays as HCl. Only at a low temperature, HCl dissociates from H class. and the chlorine minus. That's the reason that the cooling is very important. Okay, so this is just a simple things. For example, temperature 100 degree, 200 degree. This is dissociation constant change. For example, as I mentioned, 25 degree, neutral pH is 7 because dissociation constant is minus 14. But even 100 degree, dissociation constant increased to like a minus 12 or minus 13, meaning is the neutral pH is only 6 or 6.5. No? So neutral pH does not necessarily mean 7 or 6. Higher temperature, much lower value. Okay, so this shows dissociation constant of HCl. As you can see, low temperature like 100 degree, this logarithmic scale 6, meaning is almost all HCl is dissociated into H plus to chlorine minus. That's the reason we know HCl is very acidic. But when you look at here now, 300 degree, 400 degree, their HCl is not much dissociated. Yeah? As a matter of fact, more than 500 degree, almost all HCl stays as HCl. Yeah? So again, this is important because now vapor and brine fluid is a hot temperature that may not be acidic, but the shallow level now cooler. Then HCl dissociated into acid, very strong acid. So do you remember I mentioned now magmatic fluid dissociated into liquid, into vapor. Now vapor is very light, going upward. Also, even at the brine fluid compared to melt, lighter, therefore going upward. Then at the near surface, lower temperature, therefore HCl dissociated into very strong, strong acid. And we know, for example, crater lakes in many volcanoes, very, very acidic. And for example, that I cannot pronounce very well, but Tumor Murikopa, maybe anyhow, so in Indonesia, this volcano has a very acidic pH 0.3 lake water. Because HCl, because this is now surface, cool temperature, still at more than 60, 70 degrees, but still cooler temperature. Therefore, HCl is now dissociated with H plus. So, and this is a reason. For example, this is sorry, again, cut off bottom, but this is a photograph by Jeffrey Hedenquist. And this volcano, White Island, and these crater lake water is very acidic, reacting with rocks. And another example is, so therefore those water dissolve, of course, feldspars, all igneous minerals. And what is left is quartz, because the solubility of quartz, the higher alkaline conditions, therefore acidic water attacks quartz. Still quartz is quite happy to be quartz. So this is again Satsuma Iwo-jima. All those rocks are now become white, become silicified rocks, silica rocks. Okay, so I think this is a part 2 finished. Any questions? Because part 3 is alteration. around the porphyry copper deposit and the high sulfidation gold deposit, and what are implications for discovery of deposit. And also I will describe examples using alteration patterns. People found some porphyry copper deposit in Arizona and also in Chile. Okay. Any questions? Part 2. Sorry, part 2 was a bit quite heavy, and also rain was very heavy too. Any questions about part 2? Because this is supposed to be until 11 o'clock, no?
So good morning once again. So I'm just curious because you mentioned earlier about the breccias. The breccias are the
Yeah.
part where you separate the brine and the vapor. I'm just curious because in my study, I have a magmatic hydrothermal breccia in the surface. So, but how do I know that the brine and vapor separated in this portion if I will apply it into my study? Thank you very much.
It is a very good question, but there are many different kinds of breccias in a porphyry copper system. I'm sure you are familiar with the hydrothermal breccias, but also that another kind of that breccia pipes. And some of the breccia pipes are coming from a very deep level. And this is related to what is most explosive. What makes explosive? Usually, for example, something is confined for a while, and then at the release, that is the most explosive. That's the reason. This is not maybe a good example, but if you put explosive into plastic, that never become a bomb. Very, very dangerous bomb is a very tight metal container. So the pressure built up and then it's going out. So lots of things affect what kind of a breccia, how breccia is explosive, extensive. And for example, when fluid is generated in a slightly confined area or earlier hydrothermal activity sealed that area. And then that become kind of almost like a metal container. And then more and more fluid is coming up. Therefore, very explosive. On the other hand, already opened up. And then a fluid can just, release. Still maybe slightly explosive, but not explosive. But also that in this environment, I think yesterday I showed, for example, dexiltors inside of those diagrams. And also, for example, I did a study, Bingham Canyon, more than 24 lithological units identified in one place. This intrusion, this intrusion, this intrusion. And all are very similar to 39 million years, but still that different magmas coming up. And the earlier one is already solidified. Later one coming up, trying to go out, and the fluid pressure built up. So and then at the later one may make more hydrothermal alteration. So whether that is due to just a fluid separation, or most likely, but simply just those with aqueous fluid, still that volume-wise are more than that melt that produced those breccia. That's individual cases. You may have to look at breccia fragments. And also sometimes there are some breccia fragment is very rounded because obviously during the transport, lots of those aberration. And so those are, again, that all sorts of different names are given to those kind of breccias. Again, observation is very important because then yes, breccia was present, hydrothermal activity was present. Where are they focused? What is the density of the breccia? Most likely that is a focused area for the magmatism. But thank you for asking.
Yes, Professor, I just want to ask about SO2, H2S, and H2SO4 once the vapor phase separates. So is it only the oxidation? I mean, I would like to clarify what dictates the
H2S,
yes, whether which of those will.
Temperature is of course important. For example, that 800 degree or 400 degree are very different where is that boundary or H2S, SO2. But usually that around the neutral conditions, both are fairly present. But also H2O pressure is important. And for example, if H2O pressure is very high, make more H2A. So several variety. Temperature parameter is very important, and also H2O pressure, and also yes, those are And I think I did calculate, for example, that volcanic gas, how much SO2 is present, how much H2 is present. Very high temperature tend to have more SO2, even around the neutral pH.
I see. Thank you.
We have a comment from Mr. June Angeles from the Zoom platform. He said only some porphyry copper deposits have hydrothermal breccias, so we cannot assume that the cause of hydrothermal breccia is due to just water exsolution from magma. There must be a structural preparation like major intersecting structures, etc., as well as shallowness of intrusives, rapid unroofing, and others.
Thank you very much. Yes, that's a very good point. I'm not a structural geologist. I did not emphasize the importance of structure, but we know, of course, when you look at even distribution of many deposits or magmas or volcanoes, structure is very important. Otherwise, magma cannot come up from a very deep level. And and also that if you have already opened up some kind of structure, it is a fairly well known, pre-existing fault become more reactivated later on, because much easier to make opening in that pre-existing structure. Yes, that of course the structure is very important for magmatism and hydrothermal activity. And also we know, for example, many, I think tomorrow I will talk about, for example, also low sulfidation gold deposits. What kind of structural setting, what kind of faults become very important for fluid to come up. So I'm not ignoring importance of a structural geologist.
Thank you, Professor Hattori, and thank you for our participants' questions. Do we have any further question from our on-site and virtual participants before Professor Hattori proceeds with the third part of her lecture?
May I just vote?
Okay.
Yes. So third part is that hydrothermal alteration by magmatic fluids, and what are the implications for exploration. Specifically, I will describe briefly several examples how alteration patterns helped to find some mineral deposit. So some essential features of those Dixit's 2010 diagrams, and those porphyry kappa deposits formed in that area where repeated injections of those intrusive rocks at a shallow level. And as I mentioned, Singer et al. Compiled less than this is 3 kilometers from the paleo surface. And this is a very well-known textbook example of alteration patterns originally proposed by Royal Gilbert, 1970. And you may have seen this one in several textbooks. And based on that study of porphyry kappa deposit in that San Manuel and Kalamazoo. So usually those potassic alteration zones, and then at the pyrite shell or the quartz cell site, and the peripheral of propylitic alteration. And yeah, I think this is better. Potassic alteration is developed at high temperature by those brine fluid. Do you remember just I mentioned those hydrothermal, magmatic hydrothermal fluid separated into brine and vapor. Those brine produce those potassic alteration. And over 550 degrees based on the many fluid inclusion and studies. And when the temperature decreases, potash feldspar instead of potash feldspar elite forms. That's the reason those quartz cell site alteration develops. And then at further away, maybe that those propylitic alteration develop, or also those condensation of vapor makes a very acidic alteration. This was developed, as I mentioned, the San Manuel porphyry kappa deposit in what? So when Royal Gilbert examined, they found a cylindrical dose alteration, and they decided to put a cylinder because southwestern part of the United States, porphyry kappa deposit is over 60 million years in age. Therefore, upper part was eroded. Therefore, they didn't know what is present here. But now we know this upper part, something else is happening. So how those fluid evolved is recorded in a Bingham Canyon deposit through that very detailed fluid inclusion study by the Redmond. And he examined fluid inclusions in a Bingham Canyon deposit. And the very deeper part, he found those kind of critical fluid. But when you go to that shallower part, this is a paleo depth. Now that he started to find vapor phase and high density fluid inclusions. And then at the upper part, of course, all are now separated into vapor phase and the liquid phase. And this is a 0.35 weight percent of kappa conta. And this is quartz veining. Lots of quartz veining started even at when that fluid is one critical fluid. Do you remember? Solubility of quartz is mainly temperature. Therefore, quartz could precipitate, making quartz veining. So this is those pictures of those critical fluid, like so, but then at dense, those upper part, now fluid inclusion has a dense, meaning it's a dense saline. Therefore, at room temperature, you can see KCl, NaCl crystals, and also vapor. So this really that recorded when those fluid separated into dense saline fluid and vapor around this, just below 2.5 or close to 3 kilometers from the paleo surface. And so he considered this is a time when that fluid separation happened. Meaning is that this is a 0.35 kappa, this is 0.5, meaning is most of kappa likely precipitated from saline fluid, not vapor. So, as I mentioned, coarse veining was abundant all the way, even critical fluid was present before liquid separation. Meaning is this is a time when fluid started to cool down. That's the reason quartz precipitated, but not kappa much. And already I showed quartz solubility is a temperature, affected by temperature. So now explains this one. More acidic conditions, kaolinite pyrophyllite is stable. This is a potassium to hydrogen ratios. This is a temperature. So at high temperature, you have a potassium, lots of potassium, feldspar crystallize. Cooling may produce ellite, silicite. And further cooling produce more some acidic alteration, producing some smectite. But when that you have acidic conditions produce, because now kaolinite and pyrophyllite produce. So high temperature, pyrophyllite, lower temperature, kaolinite. And so usual direction is a cooling and now producing potassic alteration to philic alteration, and further just a simple cooling without changing fluid chemistry may produce kaolin, but usually produce pyrophyllite. Something happened in fluid, more acidic conditions. So now again, go back. There's a, well, it's okay. So yes, again, go back. Higher temperature, those HCl doesn't dissociate. Only cooler temperature become more acidic. That has a implication because you see this is a potassium to hydrogen ratio, more acidic, meaning going this way. So more acidic conditions, pyrophyllite, higher pyrophyllite, or even andalusite may be formed in some porphyry copper deposit, for example, that Kazakhstan, they are Conrad, they are finding lots of andalusite, meaning is a fairly acidic condition developed at high temperature. And then at if very low temperature, you can see chloride field expand, meaning is that now low temperature, potassium feldspar field is very large at a given potassium to hydrogen ratios. Now lower temperature, muscovite or mica, and if slightly more magnesium is present in host rocks, then you may produce chloride. That is a propylitic alteration. So already I talked about that. Okay. So what happened if a vapor is condensed? Very acidic. So very acidic fluid. Now kaolinite pyrophyllite is produced. As I mentioned, Royal Gilbert did not observe those very, very shallow part where vapor condensed. But for example, far southeast and many places now, we see those condensation of vapor producing a very acidic fluid, very strongly acidic fluid, dissolve minerals, except for quartz, producing such baggy quartz, textured rocks in the upper part. And also often kaolinite or pyrophyllite is present, or also now sulfur is sulfate because of very close to sulfur surface. Now alunite or kaolinite or pyrophyllite are produced in the upper part. Again, because this is now fluid, is separating a dense fluid, vapor, and HCl is dissociating into very acidic solution at a low temperature, close to the surface. So now, these high sulfidation type gold deposit is produced. Texture-wise, very, very different from porphyric copper deposit, and very different from other type of gold deposits. So before talking about those high sulfidation gold deposit, just to make sure that I will talk about what's the difference, high sulfidation type, low sulfidation type. People may hear often high sulfidation gold, no low sulfidation gold. What's the difference? State of sulfur. If you have lots of sulfur, then called high sulfidation fluid. If you don't have much sulfur, and called low sulfidation fluid. And the mineralogy is quite different. If you don't have lots of sulfur, instead of those maybe pyrrhotite, you may find pyrite, but high sulfidation, you have lots of sulfur, you may have digenite, cobaltite, lots of sulfur compared to metals. Those deposits are called high sulfidation deposits. And this shows a field where high sulfidation deposit forms. Usually, as I mentioned, they are very close to the surface, so very low temperature. So usually less than 300 or 350 degrees. So those are high sulfidation deposit has also very oxidized because of very close to the surface, and also that, as I mentioned, that now sulfur is a sulfate. So high sulfidation deposit conditions, oxidation conditions, pH are very acidic and highly oxidized. Why acidic? Because as I mentioned, now HCl is dissociated with that to hydrogen. Okay, so this is the reason. This is that some simplified diagram. Porphyric copper deposit may be present. Then above those fluid, vapor phase, going further shallower level, and then dissociating into or condensed to make HCl, very acidic fluid, making those highly porous silica-rich rocks and high sulfidation gold deposit. Okay. And but the peripheral part, this is a hydrogen to SO4, and a very, very low pH. You see those maybe alunite and the kaolinite, pyrophyllite, quartz. But then at the peripheral part, because rocks are buffering, rock contains some potassium, and therefore you may see white mica. Okay, so this is a central part. This is a more peripheral part. That is a zonation of observed in a high sulfidation gold deposit. So, and sometimes even native sulfur precipitate because low, very acidic and lots of sulfur. So now already close to 11 o'clock. My lecture is supposed to finish 11, so I will go quickly, but the alteration by magmatic fluid. So this is kind of what happened. Cooling of magmatic hydrothermal fluid, transition white mica to pyrophyllite and pyrophyllite and diaspora dicite, very acidic but very high temperature. Now hydrogen acid sulfate chloride alteration, and therefore now, except for quartz, all dissolved. And because lots of sulfur, and also remember, arsenic antimony are more likely to go into vapor phase, producing lots of energite and luzonite, and still that lots of acidic fluid, therefore producing kaolinite, pyrophyllite, and dicite. Dicite is high temperature form of kaolinite. And then at a lower temperature, now blanket of kaolinite, alunite, and very little metals. So this is some examples. There's a Iwata in a southern part of Kyushu, very residual quartz, and the kaolinite, slightly outer part, and then at some quartz alunite, and some kind of kaolinite dicite. And this is the ore body is some later low temperature. Those gold bearing fluid came to produce gold deposit. So it is very important to understand what is these alteration patterns, and then where is the center of those hydrothermal activity. And this is Summitville, Colorado, again at the quartz alunite, residual quartz. This is a place, this is a center of hydrothermal activity, therefore gold also coming later. And this is alunite, kaolinite, dicite outside. So as I said, center is a body quartz, quartz alunite, and the quartz pre-alteration outside. So maybe just I can skip this one, and I'll talk about there's some hydrothermal alteration associated with a porphyry copper deposit. And this is well described by Dixit 2016 in SEG newsletter, Valeriano deposit. And in Chile, there are many porphyry copper deposit. And again, that the lithocap was developed high iron oxide, and also that those alunite, those minerals. And this is alteration map. So these are iron oxide, very well developed. And then this is volcanic rocks. and this is alluvial later. So this is the alteration. Hydrothermal breccia. Again, this indicator, this was a center of those magmatic hydrothermal activity. Lots of hydrothermal breccia. And also that this is a quartz aronite in quartz aronite and silicite alteration. So meaning is this was a slightly deeper portion of that alteration, but this is a quartz aronite and propitic alteration, acidic alteration. So this is a vertical section. There was a quartz silicite alteration. This is related to a porphyry copper mineralization. Then at advanced those quartz elite, again at porphyry copper related, now advanced those argillic clay alteration and pyrite, energite, cobalite, those high sulfidation gold deposit. And as you can see, this is a top of those specularite. So, Argil quartz elite resuscitation. And this is those pyrite chalcopyrite porphyry copper mineralization, pyrite chalcopyrite mineralization. This is porphyry copper. And then at the top of those more acidic alteration. So this shows how alteration is very important to understand. If you stopped here, then you did not find porphyry copper deposit. So what kind of zoning pattern is quite important to find. This is a copper percent. You can see amount of copper far more because this is porphyry copper portion. So this is porphyry copper portion. This is the upper part of those acidic alteration. And of course, acidic alteration had some gold, but high is in this porphyry copper portion. So by examining what kind of alteration, advanced argillic, quartz elite, now meaning is closer to porphyry copper mineralization. So by pushing further, they found those porphyry copper deposits. So that's a fairly important understanding pattern. I can skip this one, but so examining hydrothermal alteration is very important in exploration. Distribution alteration mineral is at the secondary or primary zoning over printing. Where is the mineralization relative to observed alteration? And so just I'll show you that two examples. This is Lowell's 1968 paper in economic review. What observed is some manual segment of porphyry copper deposit because this was very close to the surface. But he believed this should be cylindrical. It should be alteration should be circular cylinder. Therefore, he believed this part is missing. What happened to this part? And what he did, because we see potassic alteration and acidic alteration, and this is a very high copper, and this is a pyrite zone. So he observed those zoning, and so this is and he found those chalcopyrite somewhere between potassic alteration and philic alteration. As I said, he believed something is missing here. This part went somewhere. So what he did, so he assumed this should be there. This is missing. So he looked at structural geology, and as I said, he believed originally here, and the entire area was tilted, and what we see is here, but this went with a normal fault, went somewhere further deep. And so his case, based on alteration pattern, predicted somewhere along this fault should have half of this porphyry kappa is present along this San Manuel fault. This led discovery of Kalamazoo porphyry kappa deposit. So he was very insightful, and he had a very strong belief, because it cannot have a cylindrical circular alteration without another half. Another good example is this resolution porphyry kappa deposit. I don't go into those details, but this is the resolution porphyry kappa deposit is here, and this is magna deposit. Magna is a kind of high sulfidation, particularly replacement type deposit. And that was already mined because of very close to the surface. And then the people did exploration drilling because there is no more ore body. So they did lots of exploration drilling. So obviously geologist was very, very observant. They noticed, interestingly, silicate quartz in those drill holes. This thought a bit odd because the high sulfidation gold deposit with some iron oxide and some kaolinite and pyrophyllite. Now they found quartz silicate. Furthermore, again, they are very observant. They noticed those quartz silicate is overprinting earlier potassic alteration. Therefore, they decided to push further. They pushed further the drilling. And this is a 1% kappa. And they had a sniff of kappa. So this one just shows lithology. But the important one is here. They have potassic alteration. This white mica is overprinting potassic alteration and the quartz silicate. So go back, several those drilling, they found silicate, they found quartz silicate. And further this one, they found overprinting quartz silicate over potassic feldspar. And that's the reason they pushed further to intersect those ore zones. They found those resolution porphyry kappa deposit. So again, those are two examples illustrate we need to be very observant. If something happens, that's a
Good morning once again. I'm just curious because I want to clarify the difference between the residual quartz and the vaggy quartz because as please correct me if I'm wrong. Residual quartz is basically have intermediate rocks that are melted from wall rock interaction. They have silica, high silica, that's why it became residual quartz. On the other hand, vaggy quartz are the leaching of your feldspars from the very acidic fluid. So I'm just curious if in the system is it the same or is it a different zoning based on the in terms of prospecting? Thank you.
Usually that those body coats, you can see through that original sometimes texture, the holes. Feldspar is, totally dissolved and very different from some simple silicification. Yes. Sometimes silicification that forms silica, but baggy coats, and also that usually those are formed in a very shallow level. Therefore, iron oxide is present, therefore very brown color, as you can see. And as I said, just very different. But many places, because they are very close to the surface, removed. Because usually that less than 300 meters from the paleo surface. Yeah.
Thank you, Professor Atori, for the answer, and Alex as well for the question. We have another question.
Good day, Professor. I would just like to ask, how to differentiate hydrogen advanced organic from heated advanced organic in the field?
Pardon?
Hypogene advanced argillic with steam heated
Normal.
advanced argillic.
Okay. So for example, that kaolinite, high temperature kaolinite is not a kaolinite, usually dikite. But also that, as you know, that many different kind of argillic alteration. Some are smectite, clay, those are low temperature. And but through that was through hypogene, not really the weathering product. And again, a bit of pattern, but very close to the surface, but usually weathering product produce also lots of iron oxide too. That's my experience in because I'm some working on that, for example, some New Zealand, these are low sulfidation, but weathering product kaolin is usually associated with some iron oxide, a bit different from hypogene kaolinite.
Thank you. We have another question from Ms. Garcia.
Good day, Professor Hattori. My question is actually about the previous presentations. Since you talked about the type of metal transporting about chlorine, H2S and OH, I don't know the implication of fluoride complexes in transporting metals, other than it reflects the source of the fluids. Does it also affect the mobility of some metals?
So you are asking metal chloride complex?
For
Sorry, Nico, can we fix the audio first?
The alteration zone or pattern, the differences between alkalic or alkalic
Yes, yesterday also I was asked, unfortunately, I'm not that familiar with the alkaline system. However, my experience of alkaline related intrusions, often are more strong, for example, magnetite and alteration, and also pattern is a bit different. That I found. But I'm sorry that I'm not very familiar. I guess I should be prepared for that. But I examined several of those alkaline porphyry related porphyry kappa deposit in Papua New Guinea or Indonesia, and also that Western Canada. And I agree that many, for example, that extent of those potassic alteration is far more sometimes extensive. But as I said, just I'm not familiar. I think my next trip, I will study those aspects.
Thank you, Professor Hattori. We have another question from John Pungo.
Hello, good morning. This question is actually for part two. Based on your experience, do you think the lithology of the host rock also affect the susceptibility to brecciation? So, like, are there certain types of rocks that experience more intense brecciation compared to others?
The brecciation and the lithology, or you are talking about? Yes, obviously that if you have a very soft sedimentary rocks, doesn't brecciate much. Different kind of brecciation, yeah. Because the hard rock is a bit more make a brecciation, yes. Yeah, so different lithology makes a difference too. Yes, I agree, yeah.
Thank you. We have another question again from Mr. Amoroso.
Just the last question. If we want to study magma fertility, what would be the best sampling practice that we could have? Would we have more samples for the fresher rocks compared to the altered porphyry stocks? Thank you very much.
So you are asking which is better to collect, or breccia or alteration, or
If we want to study the magma fertility of the
magma
porphyry,
fertility?
yes. What would we sample more on the fresher rocks, or would we sample on the altered porphyry stocks? Thank you.
But for example, that we examined the zircon from highly altered rocks, because zircon tend to stay physically, chemically very stable. And so zircon didn't have any problem. And when we like to look at what are the original compositions of magma, conditions of magma, zircon gives us some information. And if you have some raked amphibole, amphibole gives how much water, what is oxidation conditions, and so depends on that situation, but they give lots of those information. And what else minerals? And also some people examine apatite. Only problem with apatite is apatite can be easily altered by hydrothermal process, and does not necessarily that retain original magma signature. However, apatite some contains conditions of maybe hydrothermal fluid, and also some apatite may be enclosed by some hornblende, some igneous minerals, give us some information. So again, what kind of minerals are present, what the alteration mineral, what the minerals are enclosed by some other minerals, that gives us some lots of information. Yes. Right.
Thank you, Professor Hattori. We have one question from one of our Zoom participants, Jeff Pastoral from FSGRI. He asks, porphyry copper deposit may have more than one breccia. Can we use alteration to define the temporal characteristics of breccias in a porphyry copper system with respect to mineralization, perhaps?
They usually that in a one porphyry copper deposit, many different kind of breccias, and usually physically just brecciated, or sometimes even that I remember that in several of those deposits in Papua New Guinea, there's igneous rocks came up very, very fast and came up to that even at above the surface and fall back to that those area, those breccia, and also hydrothermal breccia and hydrothermal breccia or altered. So many different kind of breccias are present within one single single deposit. So I'm not so sure we can tell this kind of a breccia is a very good indicator for mineralization. Now I think that many breccia meaning is that's great. Lots of fluid was present. That gives us some potential, I think. And but then we need to have some alteration. Yeah. Because if just a vapor, probably that is very close to the surface.
Thank you, Professor Hattori. We have another question from one of our on-site participants, Mr. Barrientos.
Good morning, Professor Hattori. I would just like to ask, is there a difference between chlorine in HCl that is in molecular form and chlorine that is dissociated into H plus and Cl in their ability to form complexes with metals?
Okay. HCl or HF complexing, how different?
Cl. You mentioned earlier that HCl in higher temperatures they are HCl in molecular form. So is there a difference between if it is in molecular form or if H plus is dissociated in the chlorine's ability to form complexes with metals?
That's a very good question. But when you have metal and HCl and then after those metal likes to be together with the chlorine compared to H plus. So still that it's possible to make a chloride complex at high temperature.
Thank you.
Thank you, Professor Hattori, and thank you, Maki, for your question. Do we have any more questions for Professor Hattori, both for our on-site and virtual participants? Going once? Going twice? Hearing none, that concludes our question and answer portion. Thank you so much for all the participants, both virtual and on-site, to ask their questions. So before we proceed with the conclusion of our event, we would like to ask all of the on-site participants to come forward for a photo opportunity with Professor Hattori. May we ask the technical staff to turn on the lights? And for those participants who are joined virtually with us, may we ask you to open your cameras to join the group photo session with us.
Okay, so are we all ready for the picture? On a count of three. 1, 2, 3. Smile. Okay. Another one. Okay. 1, 2, 3. Smile. That's all. Thank you very much.
Thank you, everyone. Please stay put for some important announcements. So once again, Professor Atori, on behalf of all the participants, both virtual and on-site, we are thanking you for sharing your time, expertise, and knowledge with us this morning. Some of the graduate students who will present their thesis data to you are looking forward for their consultation this afternoon. So we are reminding all of the participants as well that the last day of the lecture series will be tomorrow, the 26th of October, where Professor Atori will discuss mineral deposits and volcanic arcs. And again, it will be done in a hybrid manner. We will have live audience, both graduate and undergraduate students, here at the NIGS AVR room. And we also have a Zoom link prepared for those who will attend the virtual session. And also, we are reminding once again our participants for the GeoCon 2022 that the last day of the regular registration will be on the 11th of November. This year's GeoCon with the theme Disruptions, Transformations, Geosciences at the Forefront will be held from December 5 to 6 or December 5 to 7, where the first 2 days will be done in a fully online manner, while the last day will feature a hybrid setup. So also before we end, we would like to ask our participants, both online and on-site, to answer a feedback form that will help us greatly improve the services we deliver. And once again, we would like to thank the following groups and organizations whose collective works made this event even more possible. First, the Office of the Vice President for Academic Affairs at the University of the Philippines, the National Institute of Geological Sciences, the Society of Economic Geologists, the Geological Society of the Philippines, and the Rush Urgent Working Group. And with that, we conclude the second day of our World Expert Lecture Series webinar this morning. Thank you everyone for spending your time this morning with us. We are looking forward to see you tomorrow for the last day of our lecture series. Stay safe everyone, and goodbye.